Alrighty, everyone. So looking at question number 5. So we already did questions 1 through 4. We started with a log, we converted into an exponential. How do we go backwards? So now remember we are going to have b to the y. B to the y is equal to x. So I have a log base b of x to be equal to y. So now if I define b will be 2, my y will be 4, and my x will be 16. So then I have log base of 2 of 16 is going to be equal to 4. Same thing here. I have b to the y is equal to x. So x is 3. My base is 27, and y, my exponent, is 1/3. So if I rewrite it, it's log base b of x is equal to y. So it's log base of 27 of 3. Here my 3 is going to be, and then my solution, my y is 1/3. So 27 to the 1/3 is going to be 3. And lastly, I have b to the y is equal to x. So it's log base b of x is equal to y. So my base in this case is 1/4. My exponent x is -2 and y is 16. So then I just plug it in. Log base of 1/4 of x is -2 is equal to 16. So then I have my x to be -2, my y to be equal to 16. So I have, well, no, here, let me fix that. There's a typo. So then y, my exponent is -2, my x is 16, and my base is 1/4. So then, yes, it's the log base b, which is 1/4 of x, which is 16, is equal to -2. Sorry about that. So let's fix that typo. Now being able to kind of go back and forth within exponentials and logarithms, I'm able to actually evaluate logarithms. So the way to evaluate a logarithm is actually changing it to exponential. So let's go ahead and do that. So we're going to change to exponential. So to change to an exponential, remember we have log base b of x is equal to y. So we were looking for the base, so the base is 12. And we don't know what the exponential is, so y is equal to 144, right? Because it's b to the y equal x. So we can change 144 to be 12 squared is equal to 12 to the y. If the bases are the same, then the exponents are the same. So the solution is y equal 2. So log base 12 of 144 is 2. Same thing here. Now you have log base b of x is equal to y. So we have b to the y equal x. So it's going to be equal to 64 to a power is going to give me 8 as a solution. Now here I have to be very careful because what do I know about 64? 64 is the same as 8 squared, but then I have an x in here, and then I have 8 to the first power. So then what does that mean? That if I have 8 to the 2x is equal to 8 to the first power, you equate exponents. So it's 2x is equal to 1. I get x equal 1/2. So my solution here, or let me change this to 64 to the y. Let me change that. So technically here it's going to be 64 to the y power is equal to 8. So it's 8 2 to the y is equal to 8 to the first. So it's just a dummy variable. So it's 2y is equal to 1. Y is 1/2. So my solution is going to be 1/2. And last but not least, I'm going to have log base b of x is equal to y, or rewrite it as b of y equal x. So in this case, the base is 3. I don't know what the exponent is, so I'm going to leave it as y, but I know that the solution is 1 over 27. Now, 1 over 27, I can rewrite as 1 over 3 to the third, which is 3 to the y, but then I can reorder this to 3 to the negative 3. It's 3 to the y, so that means that y is negative 3. So using the properties that 3 to the negative 1 is 1 over 3, so 3 to the negative 3 is 1 over 3 cubed, or 1 over 27. So all of these properties of exponents are very useful to have. Alrighty, let's look at some definitions of common logarithmic functions and natural logarithms. So there's two things. We have that the natural base y equal log of 10 is the same as y equal log of x. And y, when you have a natural logarithmic function, is log of e is written as ln. So ln of x is used for a natural log. They're both logarithmic functions, but one is identified with a different base. The natural base is e, and then the other base, the common base, is 10. So our goal is to evaluate each expression. You may also use a calculator. There's a feature on your calculator that allows you to use log, but I will ask you to compute this, making sure that I see all of the work, because all of the work is required for the test. So let's get started. So I have log of 100. So make sure that you rewrite. You notice that there's a common log. Remember, the common log is log of 10 right here of x is the same as log of x. It kind of disappears. So log of 100 is the same as log of 10 of 100. So you rewrite this as 10 to the what power is giving me 100? And that power is going to be 2 because 10 squared is 100. Same thing here. You have the log base 10 of 0.0001. So 10 to the what power gives you 0.0001. So that's 1, 2, 3, 4 decimal places where you're moving to be able to identify the solution. So if I go ahead and determine how many times do I have to move my cursor to get to my answer, then how many times was that? Was 4 times. So then so y is going to be equal to negative 4 because you're moving it to the left. Okay. Then here, now look at the base. Now you have ln, n with an e, so it's ln of e to the negative 3. So e to the what power gives you e to the negative 3. So I had to change it to exponential. That's negative 3. And then what about this one? Well, it's ln of e to the 10th. So this little base comes from this one. So ln of e to the 10, e to the y is equal to e to the 10. Well, y is equal to 10. So just rewriting and using that expression that we just learned. So what we're going to be doing is we're going to be using our calculators to find the approximate value, and we want to round to the nearest 4 decimal places. So let me go ahead and project my calculator here. Open up my screen. Hello everyone, welcome back. And for the following parts in this section, we are going to look for how to use your calculators when using logarithms and then rounding to 4 decimal places. So we'll start by doing the following. So let me go ahead and share my calculator. And then that way you guys can identify the feature. So you're just going to hit, there's your log button down here. So you're just going to put log of 200 and then close parentheses. And then your solution is going to be 2.30, 2.301, and then 10. So because there's a 2, the 2 says to stay, so as 3010. And then log, so again, down here on the bottom, log of parentheses 0.074, close parentheses. And that's going to be a negative number, negative 1.13076, but 4 decimals, negative 1.1308. Now ln is the right one below it, ln of 200. That's 5.2983. Notice that it's not the same as a log of 200, log of 200, and ln of 200, different answers. And then you have ln of 1.005, and then close it. And then you're rounding this to 4 decimal places to be 0.0049 or 0.0050. Again, making sure that you are approximating adequately. And then what we're going to do next is let me go ahead and use ln of, so if I had ln of 1.0, where's my calculator? So I have ln of 1.005. It's if I plug it in on the calculator, that's what we get. Okay. Now, the next thing is we also want to be able um, to check and reorder them. We can also switch. We can change from an exponential to a logarithm and vice versa. So we should feel comfortable doing that. Let's move on to the next part. So on the notes, the next part is to apply basic properties of logarithms. And log base b of 1 is equal to 0. Log base b of x is equal to 1. And that's because b of 0 is 1 and b to the x is equal to b to the x. So same base is equal to the same exponent. Log base b of b is equal to 1, and b to the log base b of b is equal to x. So the exponential and the logarithm will cancel. So the first thing we want to look at is we have log base b of b, right? So see how the base and the base here are the same. So we're going to use the log base b of b is equal to 1. So the first part is 1, because 19 to the first power is equal to 19. Same thing here, log of 10 is the same as log base 10 of 10. Because if we don't see a base there, that means that it's automatically 10. So 10 to the first power is equal to 10. So my solution is going to be 1. Now this one is ln of e to the e. So same thing, e to the e, or the base to the base. So we're going to use the property of log base b of b. This is also going to be 1. So for those first answers, they're all 1. Okay. Now for the next part, we have base b, right, to a 1, or let me rewrite it. We have log base b of 1 is equal to 0. So b in this case is 273, and then the exponent, or the solution, if you will, is 1. So it's going to be 273 to the 0 is equal to 1, which is correct. Now this is log base b of 1. So it's going to be, my base is 1/8. So it's 1/8 to the 0 power is equal to 1. So here the answer is 0. Here the answer is 0. Now here you have log base b of b to the x. So this b is 30, 30, 30, and then the exponent is 10. So if I have log base 30 of 30, remember these cancel, and your solution is going to be just 10 because the exponential and the base cancel. So the exponential and the base cancels. The log base b and the exponential cancels. Now 25, you have ln of e to the negative 12. Again, you have log base b of b to the x. The log and the exponential cancels, and you're only left with negative 12. So right now, all you're doing is simplifying the expression. Here you have an exponential 10 of log of 10 of 14. So, and you don't see it here, but the log has a natural base of 10. So here you have b, log base b of 14. So again, the exponential and the logarithm will cancel, so your solution will be 14. And lastly, you have 8 of log base 8 of 5. The exponential and the log base 8 will cancel, and your solution will just be 5. So we are using the properties that we just learned, those handy dandy formulas. Now for the following, what we're interested in doing is graphing. So we graphed exponentials. Now let's graph logarithms. And the first thing you want to do is actually change it to an exponential form. So we have y is equal to log base b of x. So this is b to the y is equal to x. So we rewrite it. This is going to be 3 to the y. So in this case, if we have our value of b to the y, so this is our 3. So excuse me, rewrite this to, so y is equal to b to the x, and then where did my, I think it changed to graph. Okay, so you have y equal log base b of x. Now, if we're changing this to exponential, you have b to the y is equal to x. So the base is 3. We have y is equal to x. Now, that means that our independent function will be y. So then we start with plugging -3, -2, -1, 0, 1, and 2, and 3 for the y value, not the x. So when we plug in 3 to the -3, that's going to be 1, 3 to the 3, or 1 over 27. Now your x is going to be different. So your independent value will now be y and not x. So then you have 3 to the -2. For the next one is 1 over 3 squared, or 1/9. 3 to the -1 is 1/3, like so. And then 3 to the 0 is 1. So 0, 1. So this is my x value, 1, 0. And then when my y value, it's 3 to the 1. This is going to be 3. So again, my y. So now I'm solving for x, not for y. My substitution is y now. So things are flipped. So then what we're trying to do is identify that our independent variable now is y. So when I plug in 2 for y, it's 3 squared, or 9. That means that my x is now 9 and my y is 2. 9 comma 2, 3, 1. And then over here in the negative. And then the last one is 3 to the third, or 27. That means my x value is 27, but my y value is 3. So then I notice a difference of log base 3 of x. Now for 29, 29 is a little bit different. You're more than welcome to graph this on your calculator. But as I mentioned, what you're doing now is you're choosing the values for y that will be satisfied here. So if we're interested of identifying, we're going to use the parent function log base 2 of x. And then there's going to be some shifting involved. We can use this as our parent function. And then also identify the values that we can substitute. So let's say if we plug in, what happens if we're randomly picking values for x? So let's say, can we plug in -2, -1, 0, 1, 2, 3, and 4? Well, if we're plugging in x here, you have log base 2 of 1 plus a -2. That's log base 2 of -1, which the argument is not allowed. So this is not allowed, the domain of a log. And then -1, log base 2 of -1 plus 1 is log of 2 of 0, which is also not allowed because the domain of a log. So the domain of a log, the inside x should be always greater than 0. So if that's greater than 0, when we plug in 0, we have log base 2 of 1 plus 0 plus 2. Now that's going to be log base 2 of 3. And then when we plug in, 1 second. So when we plugged in 0, 1 plus 0, it's log base 2 of 1. Oops. And then we take this and then we add a 2 for it. So log base 2 of 1, remember this is 0. 0 plus 2 is going to be 2. So the plus 2 is the k factor. So this is log base 2 of x. And then you have a plus 2 here would be the k factor. And then the 1 plus x, that's going to be the horizontal shift. So you're going to have two types of shifts here. If I have a log base 2 of 1 plus 1, and then plus 2, this is log base 2 of 2. But log base 2 of 2 is 1. 1 plus 2 is 3. And then so on. And then if I do a log base 2 of 1 plus 2, and then plus 2, then this would be log base 2 of 3, and then whatever number that is plus 2. So the remaining ones are going to be an approximation. So when I approximate it, this will be 3.6. When I plug in 3, it's going to be log base 2 of 3 plus 1, and then plus 2, so that's log base 2 of 4 plus 2. But log base 2 of 4 is the same as 2. Plus 2, that's 4. Because 2 squared is 4. And then lastly, when I plug in 4, I have log base 2 of 4 plus 1 plus 2. Again, it's going to be log base 2 of 5 plus 2. On the outside, it's going to be an approximation. You can are also more than welcome to use your calculator And then notice that you're going to be shifting, shift to the left, and then upward. So you're shifting to the left 1 unit, and then upward 2 units. So just identifying that whenever you want to graph a logarithmic function, you pay attention to the parent function. Alrighty, let's talk about the domain and range for interval notations and what types of asymptotes logarithmic functions have. So this first part is exponentials. So an exponential function y equal b to the x, the domain of an exponential is all real numbers. The range is 0 to infinity. It will have a horizontal asymptote at y equals 0, and it passes through the point 0, 1. Now, in the other case, for a logarithmic function, the domain is 0 to infinity, so the domain and the range will flop. The range will be negative infinity to positive infinity. You will have, instead of a horizontal asymptote, a vertical asymptote at x equals 0, and it will pass through the point 1, 0. So we will need the following information to solve. So it's asking us to find the domain and the range in interval notation. Well, first, the domain is that the inside of the logarithmic function has to be greater than 0. So to find the domain, x plus 3 set it strictly greater than 0, x to be strictly greater than negative 3. So my domain is from negative 3 to infinity, excluding negative 3. Now the range is going to be all real numbers. And then the vertical asymptote is going to be at x is equal to negative 3. That's when I have the restriction, because when x is negative 3, I get a 0 on the inside of my logarithmic function. Now let's look at the following. Now the negative on the outside does not affect my domain here. So the domain is, I look at the inside, which is this x. So x has to be strictly greater than 0. So that's going to be 0 to infinity without the 0. The range is all real numbers for a log. And the vertical asymptote is again at x equals 0. That's the vertical asymptote, which is going to be the y-axis in this case. Now, 32 is a little bit trickier because you have a quadratic function. So you can have log base x squared minus 3x minus 4. So you're going to create a quadratic inequality, x squared minus 3x minus 4, to be strictly greater than 0. And then you want to factor. So negative 4 and negative 3, two numbers that multiply and give you negative 4 but add to negative 3. That's negative 4 and 1. So this factors as x to the negative 4 and x plus 1. These are all boundary points that you're going to be testing. So you're going to test negative 1. And then you're going to test 4. So you're going to test what's the interval in between. This becomes a quadratic inequality. So value like negative 2, 0, and 6. And then we're going to test the interval. So when I plug in negative 2, this is going to be negative 2 minus 4, negative 2 plus 1. That's going to be equal to negative 6 times negative 1. Is that greater than 0? Yes. So I'm going to shade this area, excluding the boundary points. So excluding boundary points. At 0, I have 0 minus 4, 0 plus 1. It's a negative number. Is that greater than 0? No. So I don't shade that area. And then, of course, 6. 6 minus 4, 6 plus 1. Is that greater than 0? Yes. So I will shade this area. So then my domain is going to be from negative infinity to negative 1, union from 4 to infinity. That's the domain. And this one was a little bit more challenging because I had to factor and use my boundary points. The range, again, is all real numbers, and the vertical asymptotes are exactly those boundary points at x is equal to 4 and x equals -1. So those boundary points are your vertical asymptotes for this problem. Now, the last question for this section is an application. So let's go ahead and read the question. The absolute magnitude m of a star is the apparent magnitude m a star would have if it's placed on 10 parsecs from Earth. The lower the value of the magnitude, the brighter the star. Our sun has an apparent value of -26.74, which is the brightest night sky, and the apparent magnitude is -1.44. So notice that the sun is much brighter because it's a more negative value. So the brightness is condensed in this formula. M is equal to little m minus 5 log of d over 10, where d represents distance and 2.637 is the parsecs. And then we're given m to be -1.644. So the question is, if Sirius is 2.637 parsecs from Earth and the sun is 4.887 times 10 to the -6 from Earth, what is the absolute magnitude of the star? So the distance, it's given to us. We have two things. We have the Sirius distance and the sun distance, and we're going to look at the differences. So we're going to have a comparison here. So we have the Sirius one. The distance is going to be 2.637 parsecs. That's the distance away from the Earth. M, little m, is what's given. The apparent magnitude is -1.44. Now, our interested is identifying the value of m. So then we plug it in. M is equal to -1.44 minus 5 log of 2.637 over 10. So go ahead and punch this on your calculator, and that will determine the absolute magnitude. So take a moment and plug this on your calculator. That should roughly be 1.45. Now, if I'm looking at the Earth, or excuse me, the sun, the distance that I'm given is 4.887 times 10 to the -6. And then m is -26.74, what's given on the question. Let's go ahead and find the absolute magnitude m to be -26.74 minus 5 log of, and then keep it as is. So it's 4.887 times 10 to the -6 all over 10. Again, you are approximating this, and that's going to be equal to 4.81. So then the brightness here, it's much less bright than Sirius. So the absolute, the 1.45, shows the magnitude of the star. And with that, we finish this section. So when you're substituting D, just leave it as it is. So 4.887 times 10 to the -6, and you want to keep that in your calculator. All right, folks, and that's the end of section 3.3. Have a good one. Bye-bye.